Hi everyone. In this video we're going to talk about scale factors. A lot of the information I'm going to talk about is things you already know, but what I want to work on is how you can connect what you already know and abstract that for some different types of problems in a math class. So these are some examples I've gathered from different things you have all said. The first one is from the video clip we introduced the unit with, and just talking about Zoolander's scale model. So this is an example of a scaling and a reason you would want a scaling, which Zoolander did not understand. So the reason you might want a scale model is so you can visualize what something is going to look like, but it's too large to kind of produce the whole thing right off the bat. So we build a smaller model and we scale it down proportionately, keyword being proportionately, so you can get an idea of what that's going to look like and what the proportions are going to be. And Zoolander even talked about the scale factors here when he said, the building has to be at least 3 times bigger than this. So what he was saying there is, I want you to scale up the dimensions 3 times as big, keyword being 3 times as big. When in reality that probably wouldn't be enough to scale it, but he's still kind of knocking on that idea there. Other ideas or places you see scale factors might be in like a floor plan or a building plan, or that's kind of similar to like a map. So this is a map of ETHS. And in any map you see, you usually have some sort of like scale to tell you, 1 inch relates to 50 feet or whatever it may be. So they'll give you that so you can calculate the dimensions of the thing in real life. So this might say like this distance on the map, you might see something like this. This distance on the map represents 20 feet in real life. And you'd like take that and you'd be like, okay, if that's how long is this? And you can get an idea of like the real dimensions. And the key to that is that everything's scaled proportionately. And we'll keep mentioning that word because it's important. So another example that somebody gave is like a scale car. So a scale car is basically like a smaller version of a real car. And you might make this model so you can like display it in your house or like whatever it may be. I don't know. So I found this image and they had this notation written for each car. So I want to talk about what that means. So when it says a 1:64 scale, what that means is for every 1 inch on the model, we'll have 64 inches in real life. So anything that measures 1 inch, like if that were 1 inch, that would mean the car was 64 inches long. Or if it's a half an inch, it'd be like 32 inches long. And that kind of tells you the comparison of the model to real life. Whereas this one says for every 1 inch on the car, you'd have 34 inches in real life. And the key to any of these scale drawings is you always scale the same amount. So to go from the real car to the scale car, I would divide all the dimensions by 64. So if I divide this dimension by 64, I'd also have to divide the dimension of the windshield by 64 because you want the car to be proportionate. Or in order to like blow up this 1:24, scale car, I would have to multiply all the dimensions by 64 to make it bigger. So it'd be 24 times the size. So I would make this 24 times bigger. I'd make this length 24 times bigger. I'd make the distance of the diameter of the wheel 24 times bigger. I would scale it all proportionately exactly the same. Which proportions are really important when you're talking about like a recipe as well. So this is a recipe for chocolate chip cookies. And let's say I want to triple the recipe. Okay, I'm having a party, so I want to make 3 times as many cookies. So you wouldn't just triple the amount of cookies, you'd have to triple each individual ingredient. So I'd multiply this by 3, I'd multiply this by 3, I'd multiply this by 3, so on and so forth. I'd multiply all the dimensions by 3, so then at the end I'd have 3 times as many cookies. But you can't just like say, I'm going to make 3 times as many eggs, so I'd have like 6 eggs, but I'm going to only leave 1 teaspoon of baking soda. Then the recipe wouldn't be proportionate. You wouldn't get the same cookie. You'd get a different cookie. It probably wouldn't taste as good. So if you're scaling something, like tripling it, making it a 1:64 scale, like whatever you think about the numbers, you have to scale everything proportionately, which means everything equally. It's really important to scale something like a map proportionately because you want to make sure people can determine, real life distances. So this is a map of ETHS. It's been scaled down from its original size, so you can see it on one paper. Here's another example where you really need to know numbers. So like any road map of the country, of the world, whatever it may be, well, let's give you a scale. So this says like this distance on the map represents 100 miles in real life. So like I would try and like draw that distance on here. So this distance, let's say that's like a centimeter. I don't know, I'm making that up. Maybe 2 centimeters. I would kind of map it out here and say, okay, that distance is like the distance from Chicago to Morris, and I could say that's 100 miles based on the scale, right? So it's going to help you determine actual distances in real life if you have that proportion, ratio, everything scaled equally. And it's really important to be precise with your scaling then, because you want to make sure I know in real life, like how far is it going to be from Chicago to Springfield? I could use that scale and say, well, this is 100 miles, this is 100 miles, this is 100 miles. Okay, so it's about like 350 miles of Springfield or whatever it is. But that conversation was meant to show you that you know a lot of these ideas. And I want to talk about some vocab so we can have common language to discuss scaling. First word is a scale drawing or scale model. A scale drawing or scale model is basically just a smaller or larger version of a real thing. A drawing would be like a flat drawing, like a blueprint or a floor plan. A model might be something three-dimensional, like Zoolander's house. And it's used to represent an object that is either too large or too small to be drawn or built at actual sizes. So like, I need a small scaled down version of ETHS so I can have a map that's tangible that I can carry around with me. Okay, that's an example of something that's too large to be drawn at actual sizes. An example of something that's too small might be like DNA. Have you guys ever seen those DNA models that might look something like this? Well, the idea is that DNA is so small that you wouldn't be able to see it. So scientists use their tools to kind of be able to see it and build larger models so we can analyze the structure of DNA. So that's a model of something that's too small to be seen at an actual size. Okay, so that's a scale drawing or a scale model. Now, I want to differentiate that between what a scale is and a scale factor is. So scale is what tells us the relationship. So the key word being relationship, it's going to compare. It's going to tell us the relationship between the measurements on the drawing and the measurements in real life. So an example of a scale is when you see something like this on your road map. This distance represents 100 miles. Okay, that represents a scale because it's comparing this distance on the map to the distance in real life. Another scale you might see is like 1 inch to 7,100 miles. That should look familiar from something. So what this is another way of representing a scale. This colon means corresponds to. So 1 inch corresponds to that many miles. So this might say 1 inch on the map is 7,100 miles in real life. Again, it's comparing. Whereas a scale factor is a ratio of a length of a drawing, okay, to the corresponding length of a real object. So these are very similar ideas. The difference is this compares, and this is just one number. So example, scale factor could be like 2, or scale factor could be 1/2. Two different examples, not the only examples. But what a scale factor of 2 means is that I would multiply all dimensions by 2, so it would be like twice as big, twice the size. Whereas a scale factor of 1/2 would be something that reduces in size, it's half the size. So a scale factor of 2 would enlarge the image, a scale factor of 1/2 would reduce it. But again, a scale factor is just a number, whereas a scale is like showing you the comparison or the conversion. Okay, so make sure you have these vocab words written down so we can all talk about common language and apply it to different problems. So what we're going to do now is we're going to practice. And I'm going to have you work with the person next to you on these problems, and we'll talk about them as a class as well. So we have about 5 minutes for partner time and a few more minutes for class time. The one thing I want you to do is to change this number. It says 7 feet on mine. It says 7 inches on yours. I want you to make it feet. So cross out the inches and write feet. So all of our units are consistent. Okay, also I want to just highlight a couple words you need to know. Those words are pre-image and post-image. Pre means before. Post means after. So to pre-image, it means your before image or your starting drawing. And post-image means after or ending. So specifically, it's after you the drawing. So this is the before, this is the after. So I want you to try these with the person next to you for a few minutes, and we'll come together as a class when everyone is finished. So think about what you know from this conversation. Think about the real world examples that you've already studied or already know from real life, and apply them to some, more mathematical ideas.